got a question up here. I want you to try to find the equation of the plane containing these 3 points. Now, we haven't worked through an example exactly like that, but I have given you the tools that you need to be able to do that. So I'm going to suggest that you pause the video, try to work that out, and then tune back in and we'll work through it together. To find my equation, I need 2 things. I've got 3 things, but I need to sort of consolidate that into 3 things. So I need a point, and I've got 3 options. I can choose any of them. I'm going to choose P111. Now, if you made a different choice, you might have a slightly different version of the equation, but it should be equivalent to mine. And once we get to the final answer, I'll tell you how you can check to make sure that your equation is equivalent to the one that we get working through this together. Okay. Then I need a normal vector, because once I've got a point and a normal, I can go to point normal form. Well, if these 3 points, P, Q, and R, are on the plane, as long as they don't lie on the same line, that's enough information for me to create 2 vectors that are parallel to the plane, but not to each other. Now again, I've got some options. I think I'm just going to go with PQ and PR and calculate those, and then my normal vector would just be their cross product. Oops, because they are both parallel to the plane, so what's normal to the plane will have to be orthogonal to both of them, but the cross product of 2 vectors is mutually orthogonal to those 2 factors. Okay, so as long as these vectors are not parallel to each other, this cross product will be non-zero, and that will give me a normal vector. So let's calculate. PQ, that would be 1 minus 1 is 0, 0 minus 1 is -1, 2 minus 1 is 1. I could have used QP if I preferred, and I'm not choosing to use either QR or RQ, but that would be another perfectly acceptable option. The idea is to use the 3 points to create 2 vectors parallel to the plane. All right, now I want to cross this with PR. So PR would be 2 minus 1 is 1, -1 minus 1 is -2, and -1 minus 1 is -2. Excellent. So I'm trying to calculate the symbolic determinant. IJK, 0, -1, 1, 1, -2, -2. So I will have some i's. The number of i's I get is this 2 by 2 determinant. That's going to be 2 minus a -2. That's 2 plus 2 is 4. Then I'll have some j's. The number of j's, since I'm subtracting this, I'm going to calculate this determinant backwards. So that's going to be 1 minus 0 is 1. And then for the k's, I'll get 0 minus a -1. 0 plus 1 is 1. So a normal vector is 4, 1, 1. Excellent. So now I've got my point, I've got my normal vector, and I like to just write out my thought process behind using point normal form. Certainly you're all capable of memorizing the formula for point normal form, but I'm guessing most, if not all of you, are equally capable of forgetting a memorized formula. And so I like to understand where it comes from when I can, and this is a fairly simple derivation. So I need an arbitrary point. Now I don't want to call it Q this time because I've already used that name. So let's just say S is the point X, Y, Z. Then if I form PS, that would be X minus 1, Y minus 1, Z minus 1. You'll notice I always set this up so that I go from the point with numeric coordinates to the arbitrary point. That way, I'm subtracting numbers from my variables. Now, it could go the other way, but I think it's more complicated to be working with a 1 minus x than an x minus 1. So this is just a little bit of strategic laziness. And what I know is since this is connecting 2 points that are on the plane, it's parallel to the plane, therefore its relationship to the plane's normal is that they're orthogonal. And it's super important that that definition is an algebraic one, because notice, if I plug in the point 1, 1, 1, PS becomes the zero vector. The zero vector is orthogonal to n, and so that makes this equation true, and that makes this on the plane. Now I knew this was on the plane, so my equation had better confirm that. Okay, so let's work this out. So now we're getting 4, 1, 1, dotted with x minus 1, y minus 1, z minus 1 is equal to 0. Now, I require that you take it one step further so that there aren't any vectors in your equation. So you need to take it to 4 times x minus 1 plus 1 copy of y minus 1 plus 1 copy of z minus 1 is equal to 0. Totally fine to stop there. That's where I would probably stop. I've done point normal form. I'm going to go a little bit further because earlier I mentioned some of you might have chosen a point other than P, and some of you might have chosen other vectors that are parallel to the plane, so you might have gotten a different normal vector. Now, whatever normal vector you got, it should be a multiple of this. If it's not a multiple of this, you made a mistake somewhere in your calculation. All right, if I want to double check the whole thing, I'm going to just multiply this out. So I get 4x minus 4 plus y minus 1 plus z minus 1 equals 0. So let's see, that's 4x plus y plus z minus 6 equals 0. Or a lot of times people would write 4x plus y plus z equals 6. Now, you might not have gotten this as your final answer if you had multiplied your version of point normal form out. But what you did get should be equivalent to this. And you can tell that by both sides being the same multiple of things. So you could have 8x plus 2y plus 2z equals 12. Or you could have 2x plus 1 half y plus 1 half z minus 3 equals 0. But if you take either of these equations and multiply both sides by the same number, you're going to get an non-zero number. You're going to get an equivalent equation. And so whatever equation you got should be something that you can get to from one of these by multiplying both sides by the same number.